All right, so the next part we're going to talk about is going to be the ion product, or Q. So we talked about it back in chapter 13, or equilibrium, where we use initial concentrations rather than our equilibrium concentration. So it's kind of like a point that's not at equilibrium, but it's going to tell us kind of which way we're going to shift or how the reaction is going to proceed in order to reestablish equilibrium. Um, One thing that we can use Q for is to determine whether we're going to have precipitation of an insoluble salt. So we'll go through an example like that on the next slide. If Q is greater than K, you will have precipitation. I'll write this down. And then Q being less than K, no precipitation. So remember, K is at equilibrium, Q is not at equilibrium. So it's going to tell us kind of how we have to proceed. And remember that the concentrations they're talking about are the ones of the ions in solution. So those ions in solution, if that concentration initially is greater than your equilibrium concentrations, then some of those have to be removed or they will come out of solution to make an insoluble salt to reestablish that equilibrium. All right. So when we look at an example, here we have a solution is prepared by adding 750 mLs of a 4 times 10 to the negative 3 molar cesium nitrate to 300 mLs, 2.0 times 10 to the negative 2 molar potassium iodide. So they want to know, will cesium iodide precipitate from the solution? This is not one of the salts that they gave us information about if you read it closely. This is a different salt. So they want to know if this will come out of solution. You are given this salt and this salt. So in solution, right, you're going to have cesium plus 3, nitrate minus 1. Don't forget your polyatomics. Potassium plus 1, and iodide minus 1. So what they want to know is, will this ion meet up with this ion and form an insoluble salt? All right, so first you want to calculate your initial concentrations of both of those ions. The other ions in solution, the potassium and the nitrate, those are spectator ions. Nitrates don't make any insoluble salts. So this is kind of going back to what we learned in what we discussed in chapter 4 about precipitation reactions. So before any reaction occurs, cesium you have, and we're going to do stuff in millimoles just like we did. Or no, we didn't do any acid-base stuff. All right, so I'll quickly just go over the millimole part. When you're given milliliters, so here you have milliliters, and molarity. Remember, molarity is moles per liter. So moles per liter, instead of going from moles per liters to liters and liters to milliliters, we're going to skip a middle step and actually have something what we call millimoles. So basically, when you take your molarity and instead of liters, when you're in milliliters, dividing, you're just going to end up in millimoles rather than just moles. So you'll see that, and I'll put a little like a separate video to kind of go over those. But for now, just kind of bear with me. All right, so like I said, you're going to see millimoles, but it's just because we didn't change from liters to milliliters here. If you did here, that would be fine. So if you change 750 milliliters and down here 750 plus 300 milliliters, you can do that technically too. You should still get the same answers because at the end you go back into milliliters or molarity from millimoles, so it's not a big deal. But anyway, if you look here, your initial concentration for the cesium, this was what they gave you in the question for just the cesium nitrate, times your concentration that they gave you divided by your new volume. So really what you're doing is you're finding moles of the cesium. Once you find moles, then you're going and you're dividing and you're finding a new concentration by dividing by the combined volume. So this volume on the bottom is that new solution. So you're mixing two solutions. So your amount of moles of cesium are being dispersed amongst the new volume. So that's all they're doing here is they're taking milliliters, multiplying by the concentration, initially by itself, dividing by that new volume after you combine the two solutions, and then you get a new molarity. So that's your concentration um, of cesium plus 3 in the combined beaker. Same thing for iodate. So now from iodate, from that information, you had 300 milliliters times your concentration divided by your new volume, giving you a concentration or molarity of iodate ions in that new solution beaker. So this is after you combine those two solutions. The ion product, so Q, because we just found initial concentrations, Q is going to be, like we said before, set up the same way that K is, except you're plugging in different values. So just taking um, your ions, raising them, putting them in brackets, raising them to the power of their coefficients. If we go back, because I didn't really set up an equation here, so for the insoluble salt of cesium plus 3 and iodine minus 1, remember we dropped those charges to the subscript, so you're really going to end up with this as your insoluble salt. So to balance that iodine, that's why they have that 3 there. So that 3 gets turned into that um, power here. All right. So your Q value after you plugged in those concentrations we found on the last slide, Q is going to be 5.3 times 10 to the negative 10. So Q is greater than the solubility product constant of cesium iodate. Therefore, it will precipitate out of solution.